So, welcome to the first lecture on digital signal processing, the part of videos where we will be discussing some complex topics from the unit 1. In this, we will first of all understand how discrete time systems are defined. So, discrete time systems are defined based on input output relationship also. So, these are defined by linear constant coefficient difference equations. So, in this equation, this is a general form of equations. Of course, for causal systems, this equation is for causal systems since we are starting from k is equal to 1 or 0. So, the present output in general form is equal to past outputs, which starts from k1. So, you can understand this will be y of n minus 1, n minus 2, n minus 3. So, which are past outputs and present plus past inputs. So, this is a general form of any discrete time system which is causal, because you can understand this is y of n minus 1 and x of n minus 1, basically x of n minus 1. So, not x of n plus 1, it will be x of n plus 1 if it starts from k minus 1, but starting from k is equal to 0 means we are only looking at causal systems, which means that the present output depends on present and past inputs only, not on the future input. It is non-anticipative. So, this is a general case. Now, in the general case, if AK is not 0, BK is not 0, then the systems which are formed are called infinite impulse response systems. Similarly, if AKs are 0 but BK are some values, then this gives rise to what are called finite impulse response systems. So, we have two kinds of basically discrete time filters, IIR filters, infinite impulse response filters, and FIR filters. In this lecture, we are basically looking at how structures of infinite impulse response systems are made. So, which means that the present output will depend on past output as well as on present and past inputs. Suppose for an instance, we have a transfer function. Remember, h of z is basically y of z upon x of z. So, the transfer function of a system is given by this. So, I can simply write this because this is in plus. So, I can linearly break it. So, b naught upon this portion and z minus 1, which is delay element into this system. So, if I take the inverse Z transform and knowing that a raised to the power n u of n gives me 1 divided by 1 minus a z inverse, if this is the formula. So, B naught will be by linearity come straight forward here, it will become a raised to the power n u n. Now, with multiplication of z inverse there is a shifting. So, if z raised to the power minus n is multiplied by any transfer function, then we have h dash of basically n minus, so let it be k, so n minus k, right. So, this means that if there is z inverse, it will be n replaced by n minus 1. So, here also there is n, here also n, so it will become n minus 1 and n minus 1 and the coefficient v1 comes. Now, what is important to understand that due to un, this is from 0 to infinity and this is from 1 to infinity, u of n minus 1 is from 1 to infinity, which means to say that the impulse response is of infinite length, very important, infinite length. So, as we will see further that if in transfer function of any system there are poles, then that system will become infinite impulse response systems, just based on this part that we will have infinite duration of the impulse response due to this structure. Now, if we go further and try to make the difference equation for this equation, for this transfer function. So, what we will do? We will multiply yz upon xz to this cross multiplication, simple cross multiplication till here, and then we will take the inverse z transform. So, if it is z minus 1 yz, it will give rise to y of n minus 1. Similarly, if it is z minus 1 xz, then this will give rise to x of n minus 1. And we basically will take this portion here. So, we basically have y of n is equal to a y n minus 1 b naught x n and this thing. So, here you can see and locate that the transfer function came out to be with poles, therefore, system is IIR. Here also, due to this term, the output depends on past outputs also. The present output at nth instant depends on previous outputs, and therefore, the system is IIR system. In our general equation also, it appears to be a case for IIR system. So, with both the transfer functions with difference equations and impulse response, all three characterizations are representing that this system is an IIR system. Now, we will move forward and draw some structures. So, while drawing structures, we will use one of the three, the combination of three components. The first one is adder, very simple. If the symbol of adder is like this, then at the input of the system, if I have these two signals, then the output is basically addition of it, it's just superposition of two signals. Second one is called the multiplier. Multiplier is represented by an arrow, and over its head we put an arrow and represent the scalar coefficient. So, if input is x of n, the output is a times of x of n, it's just a scaled version. The third one is this delay, as we have seen that z raised to the power minus 1 actually represents n minus 1th instant of the signal. So, x of n is at the input, then x of n minus 1 will be at the output if it passes through a delay. So, by combining these three, we can make structures of filters. So, let me explain step by step how do we do it. So, suppose we have a difference equation y n is equal to a1 y of n minus 1 plus a2 y of n minus 2 plus b naught x of n. Now, we will draw these structures. So, to the left is the input, to the right will be the output. So, we will take input and we will try to locate the output. Now, here the output is actually depending on n minus 1 and n minus 2 instants of its components. So, we want y of n minus 1. So, from output we take a delay and take y of n minus 1 and we pass it through over the coefficient a1 and get it added at the input. So, this is for this component. We also require y of n minus 2. For that we will require another delay component z inverse, and we will have y of n minus 2 then, and will then scale it over a2 and get it added. So, this is basically the representation of this difference equation. Remember that here the input is b naught times, and therefore, we will have to multiply the input by b naught, and we need to multiply input by b naught. We can now generalize this. So, suppose for a general IIR system, the difference equation is this: y of n is equal to k 1 to n a k x n minus k 0 to m b k x of n minus k. This is a general equation. If it is a general equation, the transfer function can be represented by this, because we will take the z transform. I will take this 1 minus z. So, 1 minus poles come here and zeros come here. So, remember these bk's are actually representing the zeros of the system, and these ak's are representing the poles of the systems. So, if it is so, and as per the previous slide, you can see that here if suppose there was x of n minus 1, then we will take z inverse of this here. You can represent z inverse here and here both. So, we will have x of n here, b naught times an addition, and at this location I will have x of n minus 1 because there is a delay element. Then I will have x of n minus 2, and similarly I will have x of n minus m in this equation because the upper limit is m. So, this, and we will take the shifted versions of output, the past output. So, this is for y of n minus 1, this is for y of n minus 2, and finally a n. So, if we add this, in general case we will have this, and while drawing this we have considered that n is equal to m, which is not necessarily, but to make the diagram more uniform about the y axis, we have taken this. But the constant coefficient difference equations, which are used to represent discrete linear shift invariant systems are linear in nature. They are linear in nature. They are linear time invariant systems. Therefore, they are linear in nature. If it is a linear system, you can understand that if S1 is connected to S2, both the systems are linear. We can also implement it like this, that S2 is connected to S1, which means in the previous case, if X was the input and Y was the output, the same output will be taken at the output if the connection is reversed. So this is the basic property of linearity. The output of the first S1 is at the input of the S2, or the output of S2 at the input of S1 will give the same. So what we are doing here, that here we have zeros and here we have poles. So I am just interchanging these two. So now these are poles and now these are zeros, the same signs, the same signs. So if we are doing that, then this structure will also take X of n as input and produce Y of n as output, and still it will be like that. But what is the requirement of this? The requirement is that we can combine these, to reduce the number of delays that can be used, we can combine them. And this of course is the form when n is equal to m, for simplicity, otherwise it will not look that uniform, but you can understand this. And also remember that in the equation, this is 1 minus AK. So if you can see that the coefficients are basically minus of AK if you expand the summation. So remember that the coefficients which are used for poles are of opposite sign, and very important to note. And this is basically the zeros with the same sign, the zeros with the same sign. So this is structure. This structure is called direct form 2 structure, and since it is optimized, it is also called the canonical structure. Now look at one example to understand. Suppose I have a system described by this equation. Now with our understanding of previous examples, now you can understand that either we can work with the difference equation or we can work with the system transfer function. So I will frame the system transfer function. So we'll take Z inverse, we'll take the Z transform of the complete equation on left hand side and right hand side, and then we will take Y of Z components to the left and X of Z to the right. We'll take Y upon X to make the transfer function, and we finally have the transfer function capital H of Z is equal to 5 minus 8Z inverse 1 minus 3Z inverse plus 2Z minus 2. Now if this is the transfer function, I want to realize this system. So we will have the same system, firstly using the direct form 2 structure, direct form 1 structure. So if I am using from direct form 1, then and we'll use one delay. That delay you can represent here or here. So just I have represented it here, and we'll add it. This delay will be multiplied by minus 8 because the 0 is at minus 8 and the first coefficient is 5. And then we'll take feedback from output. So feedback required in this case will be 2. So firstly Z inverse component, the Z inverse component will be multiplied by 3 because opposite sign will come, and Z minus 2 component will also be required, and that will be multiplied by minus 2 because it is 2, so opposite sign. So then if at the input I have X of n, then at the output I have basically what I have is Y of n. What I have is Y of n. Now we can formulate the canonical structure, direct form 2 structure, the optimized structure, canonical structure. So for drawing that, again we'll take input to the left hand side, and remember in this the central positions will be the delay. So if I have one delay, to the left hand side are the poles. So poles will go, and poles will have opposite sign, which means it will be 3 times. It will go and add, and on the right hand side we will have 0. So here it will be 5, the constant term, and then the term which is minus 8. But in this case you can understand n is not equal to m. So in denominator we require 2, but in the numerator we require 1 less. So that is the advantage of this. So I have Z in minus 1 also, and that will be multiplied by opposite of this minus 2. And this is the structure for canonical structure for the same transfer function, and the number of delays has been reduced. We eventually will get the same output expression y of n. Same output expression y of n, correct? Now there are some other variants of these two structures, like we can use canonical or non-canonical to frame what is called a cascade structure. In cascade structures, we basically represent the transfer functions as a multiplication of two transfer functions and represent both the transfer functions either using direct form 1 or direct form 2. That is what is used. So suppose we have a transfer function which is given in the first equation. It is very easy to understand that the numerator is basically 1 plus z inverse whole square. So that I can write. The denominator can be broken in factors as 1 minus 0.5 z inverse and 1 minus 0.25 z inverse. So if we are framing like this, then we can use direct form 1 and 2 both. So first of all, direct form 1 case. If we are implementing using direct form 1 case, then the system S1 is basically which takes the input xn, and this is one unity, and here it will be opposite of the pole, so which is 0.5. Here it is minus 0.5, so plus 0.5. And the second is plus z inverse. No, this will be not, excuse me, this will not be 0.5, this will be 1 also. This is corresponding to the zeros. So this 0 component is also 1, so it will be 1 of the same sign. Here it will be towards this side positive 0.5. This what I have drawn here is corresponding to S1, and this is direct form 1. This is direct form 1. Now we have an intermediate output of Wn. We have an intermediate output Wn, and we again make the second system. The second system is S2, where the zeros are again on the left hand side. So this is positive. Not anything is not required. And here the poles. So the poles will come 0.25, and we will have eventually the output overall system. So this is called the cascade connection. The cascade connection. The cascade connection can also be developed using direct form 2 structures, in which the poles are to the left and zeros are to the right, and the delays are optimized. So here if I have x of n, then the poles are to the left hand side, which means this will be plus 0.5. This will be unity. You can express unity or not, because the signal line represents automatically. And suppose this is an intermediate output Vn, and this is corresponding to S2. And remember, this is S1 representation and this is S2. So if this is S2, at this side I have 0.25 and this side I have 1. Correct? And we take Vy of n at the output. So this is cascade realization of the same system, which was denoted with the transfer function. We can also use what is called parallel representation of systems. So suppose if there are systems S1 plus S2, so we can use a parallel representation of these systems. Parallel representation. So in parallel representation, we will first of all have to perform the partial fraction of the system. So partial fraction of the system has been performed. So since the degrees of numerator and denominator are equal, we need to firstly divide the both, and after division we have these factors, and we have calculated the partial fraction coefficients for the system. If this is the system, we can realize this system like this. We will take the input, common input xn, and there are basically in this case S1, S2 and S3, and all of them are added. Added means this is negative, so I will add a negative of it. So xn is taken, and we draw 3 parallel lines. We draw 3 parallel lines, and the 3 parallel lines will be representing the system. So the first one, the one which is at the top, represents the constant coefficients of 8 for S1, that will be added. The second one is representing S2, and S2 you can understand is basically, and this is basically you can multiply 18 because it is there, you can multiply it here also, and it is Z inverse and opposite sign of the pole will be added. So, this will be representation of the first order system. And remember that for first order system, direct form 1 and direct form 2 are both equivalent. Other than that, for drawing parallel realization of systems, we can use generally direct form 2 systems because they are optimized, canonical. The third system S3 is basically represented by a delay element, and that will be multiplied by 0.25, which is again the opposite sign of 0.25, and that will be added here. And for bringing variety into experience, I will write minus 25 here. You can add anywhere, it makes no difference. And all the three will get added to produce the output of the system. So, basically in this lecture, we have developed that characterization of discrete time systems can be made using either transfer function or difference equation or impulse response of the systems. In any of the are interconvertible. So, from difference equation we can come to transfer function, vice versa. From transfer function we can dwell upon the impulse response, from impulse response we can dwell upon transfer function to get the difference equation. IIR systems, infinite impulse systems, response systems are those in which the present output depends on past outputs and past and present inputs, which means that there will be poles and zeros both. So, in designing DSPs, we use structures that can be fed directly to the processor. The structures are direct form 1, direct form 2, and some combinations of cascade and parallel realizations. In direct form 1 structures, these are unoptimized, and here the zeros are to the left and poles are to the right, and they can be optimized by using the linearity property of a system, by changing the positions of the poles and zeros, and to the left comes the poles and to the right comes the zeros, and still the input output relationship remains the same, and that is called the canonical structure, which is the optimized structure, and that can be used to draw cascade structures and parallel form realizations. In cascade, S1 and S2 are combined in series combination, so to say, and in parallel realizations we have basically all the outputs getting added to give the final output. So, in this lecture we have discussed all the structures of the IIR filters. Thank you.